Hey everybody, this is a review video of the sample test I posted for our second exam. Let's get right into it. The first problem in there asks us to compare two different banks. So creatively named Bank A and Bank B. Bank A is offering savings account with 4% interest, but it's compounded quarterly, 4 times per year, right? And then Bank B is offering an account with 3.9% compounded continuously. It's usually the case that continuous compounding, sort of amplifies the effect of the compounding. But 3.9 is a good bit less than 4, so which one comes out better? Um, to calculate that, you want what is the EAYs, the effective annual yields of both accounts. The best way to think of that is it's the amount of interest the account will generate in 1 year. Whatever compounding scheme it uses, use the formula for that type of compounding and figure out 1 year's worth of interest. And my usual trick is to use $100 as the principal for the account. That way, the numbers come out as percents right away. So I think I'm going to jump right to Desmos and do that in a calculator. Um, yeah, so the first account, again, I'll use 100 as the principal. It was quarterly compounding with 4%. Whoops. Plus, so that's 0.04 divided by 4 in there. And we'll raise it to the 4t. But like I said a minute ago, we're figuring out 1 year's worth of interest. So t is 1. So 4 times 1, I think, well, I guess I'll go ahead and write 4 times 1. No, you know what? If I hit times right now, it's going to try to drop me to the next line. So if I wanted to write 4 times 1, I'd have to put parentheses around it and go to all this trouble to write 4 times 1, which is silly because it's just 4, right? Anyway, I'm going to take it out. That's the answer, 104.06. Now, I said that you could sort of read this as a decimal, as a percentage, because I use 100 as the principal. It's not that it's 104% though, right? The fact that it's 100 is that your principal is still there. The additional money is the 4.06. So that's 4.06%. All right, so let me put that answer into the exam. Bank A had 4.06% effective annual yield. I'm gonna put that there. What about Bank B? Well, let's go back to the Desmos for that. The formula now for Bank B, I'm still going to use P as 100. The principal is that, but this is the E to the RT situation with the R being 3.9%. So this is E raised to the 0.039. Technically, it's 0.039 times 1 again, but, we've got it. Okay, you can see the answer in there. 3.977 is the percentage. So it's actually a little bit less. It's more than 3.9. The effective yield is greater because of the compounding effect, but it's not enough to make up for the 4% being just a larger interest rate. 3.977, or maybe we should keep it the same number of decimal places and say 3.98. Bank B, 3.98% is the effective annual yield. Okay. Finally, which bank is offering the better deal? I hope it's clear the point of effective annual yields is to be able to compare different banks with different or different accounts with different interest schemes. And Bank A is the one that's doing better here. If you want to try to put in a little explanation, Bank A is better since the effective annual yield is higher. Something like that would be great. You don't need to do that. I was just, I'm being a try hard here. You just need to say bank A. All right, so there will most likely be a problem of this next sort, an annuity question. On the test, I will definitely give you the formula for the future value or the accumulated value of an annuity. So you don't need to put that on your crib sheets. You can if you want, but if I'm going to ask a question about this stuff, I'll give you the formula. So our job here is mostly just figuring out what things are what. Let's see. Well, let's read the words here. The monthly contribution will be $200. Got all these different variables. Which one is the 200? I hope you're saying, yeah, M. M for monthly, I guess. It's not always a monthly thing, though. And in fact, that gets us to the next number. N is in here in a few different places. Also up here in the power. That N is the periodicity of the compounding, or the number of times per year that you put in your contribution. So since this is a monthly basis, N is 12. It tells us what the interest rate is, 6%, and the accumulated values asked about 40 years from the start of this thing. So we basically need to carefully put in all this stuff into our calculator and get the correct answer. Let me point out a feature of PEMDAS, the rule for order of precedence of things that you should be aware of. It says parentheses, but it really should be any grouping symbol. Things that group all the things within them. And this long fraction bar that's in here, I can't highlight the fraction bar, but this long fraction bar is a grouping symbol. It acts just like parentheses. My advice is it will never hurt you to put in extra parentheses. So I'm going to throw in an extra pair of parentheses around our 1 plus r over n to the nt minus 1 when I go to calculate that. All right, so back to Desmos. Yeah, so we're going to have $200 was the monthly contribution times, let's see, we had 1 plus the rate divided by the period, or the periodicity, so that would be 0.06 divided by 12. That's raised to a, whoops, that whole thing is raised to a power, which is 12 times t. In our case, that is, and more parentheses that you might not think you need to put in, but 12 times 40. And here's where I'm putting in some extra parentheses that didn't appear in the formula, but they kind of are useful in making the proper grouping happen within this. We need that minus 1 to be grouped with the rate, 1 plus the rate to the power thing. All right, and then we're dividing by r over n again, 0.06 divided by 12. I happen to recognize that number, 398,298. I'm not going to bother with the pennies. 398,298. $398,298. Now, I guess if I'm being honest, they usually put a comma in that kind of stuff. You could write down the pennies if you want. Please don't write anything beyond the second decimal point. It's silly. 40 years in the future, we don't know things to that level of accuracy. Number 3 here uses the graph of f of x below to determine the requested values. Now, let me scan down here. The requested values are the limit as x goes to 1 of f of x, and then the value of f at 1, and then, same pair of things, but happening at 0. The limit as x goes to 0 of f of x, and then f at 0. It might be wise to do the second two things first, because at 0, we've got just an ordinary graph passing along the axes. There's none of this weird indication of something funny like there is here with the hole in the graph. So there, the y coordinate of the point where this thing crosses the y-axis is 1. It's not labeled, but you can tell it's halfway between 0 and 2. And so that means both the limit and the value are 1. This is a perfectly nice smooth curve passing through that thing. So as we approach the value of x equals 0 from the left, we get closer and closer to 1. As we approach the value of x equals 0 from the right, we draw closer and closer to 1. If we evaluate at 0, we get 1. So all three of those numbers are, both of those numbers are 1s. Maybe I should write equals 1 just so it looks better. I wonder if I'm allowed to copy and paste these things. I'm going to try it. Well, copied and pasted it right next to itself. But okay, there we go. Both of those are 1. Now, the value at 1 and the limit as x goes to 1 are a little harder to think about. The value, see, we've got that hole drawn in the graph. That open circle tells you, when x is 1, we don't seem to have, or at least its value isn't this number. But if you look up and down, above and below there, you don't see any filled in dots either. That means the function just can't give an answer when you put in the input 1. That means f at 1 here is undefined. The limit as x go to 1, however, it's weird because the function spits up. It can't do anything with the input 1, but for values nearby, x equals 1, it's good. It's got values. And they are approaching 4 as you get closer and closer to x being 1. When you get to 1, it says, undefined or error or something. But up until that moment, you seem to be heading towards 4. And that is what limits are for. They're to capture the behavior as you approach the point, and don't worry about what happens when you arrive, which means this spot should be 4. Let's keep moving. This is number 4. It asks us to draw the graph of a function so that the limit is undefined. That's actually easy because it doesn't say anything about the function other than that. The limit as x goes to 0 should be undefined. Here's the axes. That's the y-axis. Here's the x-axis. What we need is, as you approach x from the left, you should get some value on the limit. And if you approach x from the right, or 0 from the right, you should get some different value. So if I had something like that, whether these were filled in circles or one of them was filled and one was open, that would still be no good for a limit. The limit as you approach 0 from the right is, well, it looks like about -0.5. And as you approach it from the left, it looks like it's closer to 1. So the point is they're different values. So that's a fine example of a graph that has no limiting value at 0. It's also apparently undefined at 0, but it didn't say what else we had to do, just that we didn't have a limit as x goes to 0. Number 5 asks us to evaluate some limits. Let me point out that when you're evaluating limits, the very first thing you try is see if you can stick x equal the number in, right? This one is asking for a limit at 0. Well, what happens if you stick x equals 0 into this formula? You're going to get x 0 squared minus 1 over 0 minus 1, which is -1 over -1. You don't have any work to do. That's going to be equal to 1. This one, on the other hand, well, they factored it for us, so it's not quite all that bad. But look what happens if you plug x equals 2 in. In the numerator, we'll get a 0 from that factor, and in the denominator, we'll get a 0 from this factor. And so we'll have 0 over 0, even though these other things weren't. But if we cancel those things, you're just going to get x plus 1 over x minus 1. I think I, again, want to write this out for you. So we have the limit, x approaching, I forgot where it was approaching, 2. X is approaching 2 of, Well, I guess I'll do the cancellation first. We end up just with x plus 1 over x minus 1, right? And once that cancellation has happened, we no longer have 0 over 0. In fact, you can plug in 2 into the formula. And here, in the top, you'll get 3, and in the bottom, you'll get 1. So that's 3 over 1, but that's just 3. Yeah? Cool. The last problem on there, let's go back and look at the PDF. It's x squared minus 1 over x minus 1. Again, I'm going to jump over to the document cam here so I can write that stuff for you. That's the limit with x going to 1 of x squared minus 1 over x minus 1. So here they didn't do the factorization for us, but you probably noticed that the numerator there does factor. So we end up with the limit, same limit, x going to 1. The numerator factored is x plus 1 times x minus 1. And then we have the x minus 1 term that's down in the bottom before. And those two x minus 1s can be canceled. I should point out the sort of theoretical thing that's going on here. When you divide by some term, in other words, and when you cancel terms in a rational expression like that, it's effectively division. What you're assuming is that the thing you're dividing by is non-zero. And, well, that's okay for us here, because when x minus 1 is 0, x must be equal to 1. And when we take the limit as x approaches 1, we don't care about what happens when x is equal to 1. We just want to know what happens as x approaches 1. So while you're doing this limit stuff, you can assume that x is not equal to 1. That means it's perfectly legal to do that crossing off, right? But it's really nice because we're in a situation now where I can just tell you what's the value. This is, I guess I'll write it one last time as the limit with x going to 1 of just x plus 1. That's something that we can literally fill in, plug in the x, the 1 and 1. Oh, we're getting 2. When you're supposed to learn calculus and you're doing 1 plus 1 equals 2. But yeah, okay, that's silly, but yes, that works. Next up, we have some derivatives to do. Let's see if I can write them without having to resort to the document camera. That first one's real easy because it's 4, right? This is a line, 4x minus 12. It's got an m of 4 and a b of minus 12. What's the slope of a line? Because the derivative should be the slope, essentially, of the graph. For a line, the slope is always the same. You've got just the number 4. Now, if you wanted to use the power rule here, you could. Think of that as 4 times x to the 1. So x to the 1's derivative would be 1 times x to the 0. That actually is 1, because anything to the 0 is 1. And so we have 4 times 1 there. And the minus 12 doesn't matter, because whenever you have a constant, you kill it. It dies when you take the derivative. Its derivative is 0. What about this next guy? X squared minus 100. Well, my comment about constants being unimportant certainly holds here. This minus 100, you don't need to worry about. The actual derivative is just the derivative of the x squared part, and that is 2x. You bring the power out front, and then you reduce that power by 1. It's not necessary to write 2x to the 1 power, though, right? Because anything to the 1 power is itself. And lastly, just to check that you know how to deal with sums. This is one of they call it the sum rule, although there's also a difference rule. But the derivatives should be just, how to say it? Just take the derivative of each piece of that thing and add them up. So we'll get 5x Can I do subscripts, superscripts in this? I'm afraid I can't, but I'll just write it like that. At 5 times x to the, 4 plus 3 times x to the, what power will be on the x for that middle term, squared, and then the derivative of x, which is simply 1. I'm sorry, that lapped funny. I gotta move it around. Cool. So that's us doing derivatives. What's next? More derivatives. Now, this one is a graph of a function is given, and you are supposed to approximately, not perfectly, but approximately draw the derivative here. Indicate the places where your estimate of f prime of x is 0. That's a good place to start. See, what I want to do is, do you see that at that hump in the graph, its tangent is essentially 0? That is, its slope for its tangent is essentially 0. It's a flat spot. If you were walking on that, you'd detect that you were on level ground. If you walk over a little to the right of that spot, you'd go, oh, I'm going downhill. And if you were a little to the left of that spot, you'd say, oh, what a climb, I'm going uphill. But right there, for a moment, you're not changing altitude at all. You're just moving horizontally. There's another spot down here. Those spots are where our derivative should be 0. So if I want to try to fill in a spot on the x-axis, it'd be like right about here. And just below this location, another spot on the x-axis that would be right about there. Now, the other thing we're going to need to do to figure out, what's the derivative look like is notice when is our graph going up and when is it going down. Because an increasing graph, as you move left to right, has a positive derivative, and a decreasing graph has a negative derivative. So the sign of the derivative in here is positive right there. It's negative in this part, in between the two zeros, and it is positive again out on this side, which turns into fairly nice information about the derivative. The derivative should be up here like that. It should drop below the axis. Oops. It'll be negative there, and it'll be positive out this way. And unfortunately, I don't seem to be able to make it hook together, but this would really be a continuous curve. Maybe the smarter thing for me to do would be to erase that stuff and start from scratch, because if we draw it all in one fell swoop, it'll be good. Huh. Yeah, that's kind of it. Anyway, it only said approximately, so that's pretty good for an approximate graph. I would give that 100% on the test. You can probably do a better job of drawing it nice and smooth than I just did there, but that's close enough. All right, problem number 8. We got a little more work to do on document cam, I think, because this one is going to require us to write a few things. All right. Let me first say there are a couple of things that you should definitely make sure are on your crib sheet. These rules for derivatives: the product rule, the chain rule, and the quotient rule. Now, I'm doing something that is somewhat bad, writing f times g rather than f of x times g of x. The rule is just quicker to write down that way. The only one where we really kind of care about the of x part is the chain rule, because there is a distinction between what's happening with g and what's happening with f here in terms of its inputs. But f and g in these other two rules, they're both of them evaluated at x. Anyway, the product rule looks like this. The derivative of the first one times the second one, with no derivative on that, plus the first one times the derivative of the second. Make sure to put that on your crib sheet. The middle guy is maybe conceptually and also in terms of the shape of the formula, the hardest to deal with. Let me point out, though, that it looks like you just multiply f prime times g prime. In fact, it's what a lot of people kind of wish the product rule was. Shouldn't you just take the prime of the thing and its derivative and multiply them? No, you got to do this. But when you're doing the composition of one function with another and you want its derivative, that's the product of f prime and g prime. Except the problem is, you notice how I left just space to fill in where they're evaluated? They're not evaluated at the same place. Over here, g of x was evaluated at x, and that's where g prime will be evaluated too. But f was not getting x as its input. It was getting whatever g did to x as its input. So f prime needs to be evaluated at the same place f was, which is g of x. That's really just f prime times g prime, but evaluated in different places. Lastly, the quotient rule, f over g. Well, that is the derivative of f times g. You notice that's the same thing as in the product rule, f prime times g. It starts with the same exact thing, but it subtracts instead of adding. And then you actually have the same other term, f times g prime. So that's the pretty good if you write the derivative, if you write the product rule. Sorry, I haven't put the prime on this thing. If you write the product rule in that way, just kind of stick to it systematically, always doing the same thing, then the quotient rule, same problem. I need to say take the derivative of f over g. You know, it has the same terms in it, but the plus is a minus. And there's one other difference, which is you need to have a division by the square of the lower function. That's just the way it is. I view that as the hardest one to memorize. Memorizing it isn't necessary for you guys because you can write it on your crib sheet. Okay. Well, let's put these babies to use. The functions we had to deal with were, first it was x squared times e to the x. And I hope you see that that is a product. We take the derivative of that, we get, okay, f prime times g, that's x squared's derivative times g, which is e to the x, plus x squared left unchanged times e to the x's derivative. Well, we should know how to take both of these derivatives. X squared is a power rule, and the 2 comes out front, you just get 2x. E to the x from that other piece of it. Here then x squared, oh, but now we need the derivative of e to the x. And if you haven't run into this yet, you should be getting that in this last batch of homework. The e to the x is this weird function that when you take its derivative, you get itself. It's the only one that, well, other than the 0 function, I suppose, it's the only function that is its own derivative. So there you go. That is a good expression for the derivative of that product. There is a little bit of a temptation to try to simplify that, but please don't. I think you'll find that it's, well, it's easy to mess up in doing the simplification. If you write it this way, it looks like you used the product rule, right? I mean, you see the derivative of x squared, and then you see the x squared unchanged. And okay, e to the x and e to the x, you can't tell which is the derivative. But when I'm checking this, it's way easier for me if you've written something that looks like you used the product rule. So please do that. Our next problem had x to the 5th. I should have probably numbered these problems. This was Roman numeral 1, Roman numeral 2. X to the 5th plus x cubed plus x raised to the 5th power. And we want the derivative of that. Well, I guess in compositions, I often think of it as the outer function, the outside, and then the inside. The outside here is raised into the fifth power, and the derivative of fifth powering is 5 times fourth powering. Right? I left the blank there because what's supposed to go in this? The exact same thing that was in the outside function before, namely the inner function, which is that polynomial, x to the fifth plus x cubed plus x. And then remember this guy? We just did the f prime times g of x part. My bad. I should have said f prime of g of x. We still need the g prime of x. We actually did that derivative in a previous problem, so it's 5x to the fourth plus 3x squared plus 1. And again, if you're tempted to simplify that, try to resist it. Written this way, I see, okay, that person knew the chain rule and they wrote it down right. So don't try to do any simplifying that might approach that you might see. Leave it as something that looks like you did the right thing. I think I'm going to switch pages here. Third subproblem in this guy, number 3, was e to the x over x. So that's the top is f, the bottom is g when we do that quotient rule. So we will have e to the x's derivative times g times x minus e to the x times g's derivative all over g squared. Actually, e to the x prime, I left the prime off there. But you know what? I might as well have left the prime off because e to the x is its own derivative once again. So if you work out what the two things that we need to do to differentiate here, this one becomes e to the x, and this one becomes 1. So you get, we have to change the order and write it as x times e to the x. That's kind of the normal approach. If you have the e to the x, you put any polynomial or power thing that goes with it out front. But this will be minus 1 times e to the x, so that's just e to the x. And in the bottom, x squared. Well, okay, we've got a function, x cubed minus 3x squared minus 9x plus 1, restricted to the domain from minus 5 to 5. And asks us it asks us to basically do the calculus computations. Find all the critical numbers. From the critical numbers, you'll find the relative min and relative max, or sometimes the local min and local max. Those are synonyms. But it doesn't even ask about those. It just says find the absolute min and absolute max. Basically, that just means in addition to these things we find in step 1, the critical numbers, we'll look at these two endpoints, minus 5 and plus 5. And saying where the extreme values occur just means also mention the x coordinates, although it's fine to write those as points too with an x and a y. I think on this guy, we want to switch over to Desmos. All right, so the function x to the third minus 3x to the second minus 9x plus 1. In both Desmos and GeoGebra, there's a way to do this. In GeoGebra, it's slightly different. In Desmos, it's curly braces. This is what lets you draw just a limited portion of the graph. So we want the part between minus 5 and 5. So you just write in that inequality. And you see that we've only got part of the graph. Now, I kind of want to get this to the right zoom level so it more or less fills the screen. I guess that's as good as I can do. We also are going to need the derivative of this thing, which I can go ahead and type into Desmos. The derivative is 3x to the second minus, what's 3 times 2? That would be 6x, and then minus 9. That's our derivative. The plus 1 gets killed off. That should actually be restricted to the same domain. So minus 5 less than or equal to x less than or equal to 5. Well, but really what we care about is where is the derivative 0? And on the Desmos graph, you can see 2 places where that happens. When x is 3, that happens, and also when x is minus 1. You might want to figure out how to do that with your own brain instead of the computer. So let's quickly look at that. The derivative we had there was 3x squared minus 6x minus 9. You should spot that there's a 3 in each of those, so you can factor a 3 out. And then you're left with x squared minus 2x minus 3. Does that thing look like it factors? I think so. You got to work your way through the unfoiling of that. It'll be x plus something times x minus something. How do I know that? Well, because the last times last gets us a negative number. So I'm looking for 2 numbers, one positive and one negative, that multiply to give us 3. It's probably 1 and 3, yeah. But we also need the outer times outer and the inner times inner to end up giving us this minus 2x. So I believe the 3 has to be the one that's subtracted and the 1. Does that do the trick? Well, this is guess and check moment, right? Positive x minus 3x, that's negative 2x. We're getting the same thing there. Last times last is indeed minus 3. First times first is x squared. I think we got it. And that factored form tells you that x is equal to minus 1 is one place where you'll get 0. And the other place you'll get 0 is x equals to 3. Cool. Let's run back to Desmos, and that definitely agrees with what we found over here, yeah? Okay, so we have to basically find out what the values of this original function, the blue thing, f of x, is. Oh, I better name that something so I can use a little shortcut. F of x equals that, rather than just writing in the expression. I'm going to create a table. I like doing this in Desmos. The x coordinates where I want to look at things are minus 5, one of the endpoints of our interval, and then negative 1, that's one of our critical numbers, then 3, and finally plus 5. So we've got our 2 critical numbers, minus 1 and 3, and our endpoints of the interval at minus 5 and 5. And what we want to do is make the second part of this table just be evaluate the function at the numbers that I just gave there. And in fact, it's drawn them for us, and you can see which one's the highest and which one's the lowest on this. So what is our global high value? It is 6. It's the y-coordinate of that point. Happens to also be the y-coordinate at this point. That global max happens in 2 different places. The global min, negative 26 here, but negative 154 over here. That minus 154 is much more negative, much smaller. So that's the absolute minimum, and 6 is the absolute maximum. We should just say, filling out everything. The absolute max was 6. The absolute min that was negative 154. Max occurs, 2 C's, occurs at, well, it was two different places. One was -1, and the other was x equals 5. Oops, off the page. Sorry about that. And then the final thing for this problem, where's the min happen? The min occurs at x equals -5, the left-hand endpoint of our interval. Okay, this is a really a useful sort of problem, the microeconomics of a small company. Let's talk about a couple of things here. One is they've given us the relationship between price and how many items you can sell. P of x is called the demand function, although actually P stands for price. So it's a slightly weird thing. You think that a business has control of what price they charge, and honestly, that is the case. But we like to think of it as sort of tell me how many you want to sell, and I'll tell you what price to set it to get that. Either way, there's a relationship between price and the quantity you'll sell. In my way of thinking things, this gets it slightly backwards, but yeah, it is what it is. If x is 0, that means what price should we set to make so that nobody will buy anything? I think this is $1,140. Whatever our product is, if you charge that much for it, they're going to sit on the lot. You will not get anybody to buy even one. If, on the other hand, if x is 1,140, this formula would give you 0, which is an interesting point. If the price was 0, how many would you sell? Just 1,140. So the limiting values, or sorry, I don't mean limiting in the calculus sense, but the sort of end of the range values for the P of x function are interesting. They tell you how much you can sell if you make the price 0, or give the things away, and you might be able to, really probably be a larger number. In fact, this is generally not a linear function, but often it's linear in a reasonable range, so we do that. Does everybody see why I'm saying linear function? That's 1140 minus x, a b of 1140 and a slope of -1. Anyway, revenue. Revenue is simply how much do you sell times how much you sell them for. That is the price times the quantity x. So here, let's just do this with typing. It'll be P of x times x. If you are interested in revenue and taking derivatives and stuff, you need the product rule for this. So it's a real place where it's appropriate to multiply two functions, and you get a thing that if you need to find the marginal, you'll need you'll need a product rule. What about the profit function? All too often I see people in business calculus who don't know this, so I want to make sure that you guys know it, right? Really, I want you to know it thoroughly. Profit is equal to what you take in, which is, the revenue function, minus what you spend. Profit is that. So for us, in this particular function, in this particular situation, we're going to have 1140 minus x times x, that whole thing times x, and then minus all of this stuff. Our profit function, P of x, is two things. X times the price-demand relationship minus the cost. Now the cost had a bunch of stuff in it. So all of these things are going to be subtracted. 7,600 plus 380x plus a half, or 0.5, of x squared. If you know the terminology about fixed and variable costs, that's what you're seeing in here. 7,600 is your fixed cost, and 380 is a cost per item sold or per item produced. That's a variable cost. There's also a quadratic term in here. That's the sort of thing that usually people say that's the inefficiency term. You do have, well, you have extra costs that you incur just because you're trying to do too much. Like maybe you have to pay the workers overtime, or you have to not seek out the best deal on your ingredients because you just don't have time for that. So you're willing to accept less than optimal prices for things that go into your product. Yeah, that kind of stuff all has generally a quadratic dependency on the product or the production level. All right, so if I try to simplify all of this, I have 1140x minus x squared. Watch out, all the remaining things are negative, or subtracted. So 7,600 minus 380x, and then minus 0.5x squared. That all should be simplified. We should combine the like terms. You see that the highest power is the second power, and we've got a minus x squared and then a minus a half x squared. So that's just negative 1.5 x squared. The next highest power is x to the first power. 1140 minus 380. Okay, that was 760 x. And then finally we have this is the only number, right? Only constant, minus 7,600. Quick edit. I messed up the sign of that term, so it's actually plus 760x. And that the next thing we're asked to do is find the marginal, which is just a synonym for taking the derivative. So we want p prime of x. That would be negative 1.5 doubled, gives us negative 3 times x, and then 760x gives us plus 760. And the 7,600 being a constant goes to 0, so we don't have to deal with that. So there's our marginal. Often in problems like this, they will the next phase will be to say, well, now what value of x is going to give you the maximum profit? And that's just figuring out where is this derivative 0. So it would be at 760 divided by 3. Let's do the last one. Now for this, we're definitely going to need to make some pictures. This is an application of calculus. There's a lot of these applications to sort of agriculture, where you're animal husbandry, I suppose. You're trying to find the best way or the cheapest way, or the maximum area is a very common one. But let's go with it. We have a situation where there's a natural boundary, a river. Well, I was surprised to find out recently that cows do not have a problem with rivers. They'll go right into them and stand around in the water. But maybe there's some other animal that's afraid of water. So anyway, we're going to make a enclosure for these animals that takes advantage of the natural boundary. So we only need fence on 3 sides. And here, I'll draw some water out here. Does that look like water? Anyway, the thing to do is first notice that you've got 2 different lengths of the sides of this thing that are the same. They're equal to, I'm calling it x. And then there's a third leg that's its own length. And the total of those things, it was part of the word problem, was 1,000 feet. So that is 2x plus y equals 1,000. A thing like this that we've just written down is known as a constraint. That was a constraint. That's not the thing I'm trying to find the max or min of. It's just part of the rules of the game. If I only have 1,000 feet of fence to work with, I can only use 1,000 feet of fence. But I still want to make the area that my animals have to walk around in and eat be as large as possible. Because right there, they're going around cropping the grass inside of that region. Okay, well, what is it that I'm trying to find the maximum of? It's area, and you should know the area formula for a rectangle. It's just how wide is it times how tall is it, or length times width. But in this case, it's x times y. Now the thing that's cool about this constraint, actually, let me just do that first. You can solve it for either one of the variables, but it's easier in this one to solve it for y. And you get y is 1,000 minus 2x. And so you can write a equals x times y, but you can also write y area is equal to x times that expression, the 1,000 minus 2x that I just solved for y. Why is that good? Well, now I've written a strictly in terms of one variable. There's no y's anymore. It's just a single variable x. And yes, I can do the calculus on this formula. I might want to simplify it first. It's 1,000 x minus 2x squared. So what do I mean by do the calculus? I mean take the derivative of it, figure out what a prime is. It'll be 1,000 minus 4x, and then solve where is a prime equal to 0. That's when 1,000 is equal to 4x. And so that's dividing both sides by 4. That gives you x is 250. Now you can, you should note there's a couple of ways to proceed now because you want to say what y is as well. Let me come back up to the thing here. So you notice we've solved for y before, 1,000 minus 2x. So if x is 250, twice it is 500. 1,000 minus 500 would be 500. You might also just go, okay, 250 here, 250 here, what's left? 500. That is, you don't necessarily have to do the algebra. There's our two values. X is 250, y is 500. Okay, well that is it for me on this review. I will be, as last time, posting some extra office hours. I think probably on Saturday, and I may have a few tomorrow as well. All right, ciao.